Right, okay. Want to talk about a couple of these questions from this exercise on damped harmonic motion at the moment. So I'm looking at question 2 there. Okay, line paper here. Right. So the particle's moving in a straight line, and basically we want to solve this differential equation. So we've got d2x dt squared plus So I'm gonna get the auxiliary equation out. Okay, so this is d2x plus dt squared plus 8dx plus dt plus 12t equals 0. Okay, m squared plus 8m plus 12 is equal to 0. So that's m plus 6, m plus 2 is equal to 0. So obviously m is minus 2 or minus 6. Right, okay. And then that tells us then that x is equal to a e to the minus 2t plus b e to the minus 6t. Came out nice. Right, okay, and then when t is 0, p is at rest at the point where x equals 4. I want the x dt then, don't I? Because it's at rest, we know that. So dx dt equals minus 2a e to the minus 2t minus 6b e to the minus 6t. Okay, and t equals 0, we've got x equals 4. So 4 is a plus b. Right, they're 1, aren't they? Okay, and when t equals 0, dx dt equals 0. Okay, so 0 equals minus 2a plus 6b, and then just solve these simultaneous equations. I'm going to do twice that plus that. I've got 8 is equal to, I said twice that plus that, didn't I? Is equal to 8b, so b is 1. So a is 3. Does that work? Minus 6 plus 6, yeah. Okay, so our not y. Our function x is 3 e to the minus 2t plus e to the minus 6t. What's that? It's over damping, and you want to know what the graph of that looks like, really. So you can draw that if you want, but really over damping, which is this equation having two real distinct solutions, it's just like that. That's all it is. It's indistinguishable really from just one of these exponential decays. Okay, right, that's question 2. I want to look at question 4, right? So question 4 is it's nice context here about the spring. So at time t equals 0 to projected downwards at speed u. Okay, right. So again, like what I'm finding here with their questions is, the question basically just says solve this differential equation, which is fine, but all that there we're nice little context there. The resistance is proportional to the speed of p. That's this 4k dx with dt, and that's what I was talking about previously, where it's in the opposite direction to the acceleration. It's nice that, but let's have a look at trying to answer this question. So we've got d2x with dt squared. I like this because it's got variables in rather than just numbers. Plus 4k dx with dt. I do like that. I don't mean it's, I'm not appealing to like, oh yeah, let's make it hard. I just mean I like it being quite general. Equals 0. Right, okay, so find an expression for x in terms of u, t and k. Right, well, first of all, let's solve this. So m squared plus 4k m plus 4k squared equals 0. That's crying out for completing the square, isn't it? Minus 4k squared plus 4k squared equals 0. Oh, of course it is, it's an perfect square. So it's just m plus 2k squared equals 0. So m equals minus 2k. So what have we got? We've got x equals a plus bt e to the minus 2kt. Okay, this is critical damping. It's critical damping because even though totally blind not to see it straight away, but this is got a repeated root. So there's the repeated root, and then this is the equation that you would draw in. It would look like critical damping. So dx dt, let's differentiate this then. So this is product rule, isn't it? So it's firsty second plus secondy first. So we've got minus 2k a plus bt e to the minus 2kt plus secondy first b e to the minus 2kt. Okay, that'll do. And then when t is naught, I'm just looking to see what it says. Oh, it's at the equilibrium position. Okay, so when t is naught, x equals naught. Okay, so we've got naught equals a. Yeah. Naught equals, yeah, this is naught. This is 1, so it's just a. That's good. Okay, and when t equals naught, x equals... sorry, the x dt equals... I don't know. I'm going to say u. I'm not sure if it's u or minus u, but let's go with u. And basically take that direction to be positive, the downwards direction to be positive. Let's see what happens. Okay, so we've got u is equal to... what's going on here? Oh. I'm not sure if it jumped in the middle there because my battery went low, but I'll hurry up anyway. So u is equal to 2k times, that's naught, right. U is equal to b. Okay, so we've got x is equal to ut e to the minus 2kt. Okay, and that does strike me as being, well, it's critical damping, because it'll look like this. Okay, so when t is really small, this is approximately, that should go through naught. Oh, rubbish. When t is small, it looks approximately like y equals x, and when t is large, it looks approximately like y equals e to the minus x. So that's your critical damping, but as I say, it's not very different to over damping. Right, okay. And what does it want? It wants the time at which p is at instantaneous rest. So we want the x dt to be naught. So the x dt is equal to 30 seconds. So minus 2k u t e to the minus 2kt plus secondy first. So plus u e to the minus 2kt. And if that is naught, I'm just going to factorise that. What can I take out? U e to the minus 2kt into minus 2k plus 1. Okay, when that's naught, the dt equals naught. Obviously this is never naught, so this is naught. So we've got minus 2k plus 1 equals naught. What am I talking about there? Minus 2kt. Minus 2kt plus 1 equals naught. So t equals, I can't do this in my head, 2kt equals 1. So t equals 1 over 2k. There we go. Okay, and I'm sure that's the right answer. Right, okay. Yeah, good.